Okay, you are live on Facebook and successfully being recorded. So go ahead when you're ready.
All right, thank you, Christine. Hello, good morning, everybody. My name is Michelle Crepeau, and I am the Museum Conservator for the North Carolina Maritime Museum System. That means I am basically the artifact doctor for the maritime museums. I basically, as a doctor would, give our artifacts checkups, make sure they're not experiencing any health problems. And if they are, I help design and implement treatments to make them feel a little bit better, so we get to keep them for a longer period of time, and they can continue to do their very important jobs in our collections, communicating stories about the past to our visitors, to researchers, etc. And as long as we can keep them doing that, I'm also in charge of their long-term welfare. And I also help out the education department from time to time by giving these science-focused lectures about various topics in archaeological conservation. Sometimes they're a little bit dry. I'll try to keep them a little bit lively or a little bit more accessible. Today's presentation is entitled Get the Lead Out, Conservation Basics number 5, and it deals with the topic of lead chelation and archaeological conservation. So this is specifically a treatment that we use on a lot of lead artifacts, particularly ones from saltwater or marine burial sites, but we also use them quite frequently for any type of archaeological lead that has been buried in the ground or the ocean. All right, so to start, lead is a very old metal in terms of being known to humans and being used by people. There are some records of it being used as early as over 7,000 years ago. The Turkish site of Çatalhöyük, for instance, there's records of metallurgy involving lead happening as early as 6,500 years ago. So it is definitely a very interesting, relatively abundant material that we use for all types of products. You might recognize it from, in terms of raw lead. We use it in our piping. We use it to make bullets and other types of material culture. It's in electronics. It's even in pigments that we use in paints and cosmetics, as well as in things like glass, etc. So it is quite a very versatile type of material. It is not, however, in pencils. Pencil lead is not actually lead. It is a form of carbon called graphite. So that is a misnomer. So I just thought I'd clear that up. There is no lead in your pencils. Although, as we'll see, lead has been a pretty important component of writing for centuries. So lead is a pretty abundant material on Earth. It is, I think, number 16th in terms of the most abundant metal available on the planet within the Earth's crust. You can find it as metallic lead, so already pretty much pure lead. However, it is more commonly discovered in various types of minerals such as galena, anglesite, and cerussite, which are, you got basic lead sulfides and sulfates and carbonates exclusively. So we'll see these guys kind of pop up in other contexts, but essentially these are the forms of lead that we tend to find. So what makes lead such a great material? Why did early humans first start using it before a lot of other metals? One of that, besides its abundance, is it has a very low melting point, 327.5 degrees Celsius or 621.5 degrees Fahrenheit, which is essentially the temperature of your average wood-based fire. So you can see this is a very easy metal to melt down and then to purify, to basically extract it from its ore content. It's pretty easy to extract it since it has such a low melting temp, and then basically refine it into metallic lead, and then use that metallic lead to, again, melt it down and use it for things like casting. So it is a very, think of tin cast soldiers and other types of paraphernalia that are made of lead. It's a very easy metal, and bullet molds, we have some of those on display, in fact. It's a very usable metal that is very easy to work with at low temperatures when you don't yet have the technology to create heat sources that far exceed your average wood burning surface. In comparison to iron, which has obviously a much, much higher melting temperature of 1,538 degrees Celsius, also 2,800 degrees Fahrenheit, which is about your average blowtorch heat. So you can see sort of the juxtaposition is that obviously one metal is a lot easier to work with. Also, even at room temperature, Lead is very malleable. It's a very soft type of material. It's very easy to work cold. So you can actually manipulate lead, work it, bend it, etc., without needing to heat it, which means it's a very easy metal to work with. And it also makes it easy to work with on situations where you can't use fire, like on board ships, for instance. We often have a lot of lead that was on board on ships. It was made out of everything from basically caulking, reinforcing and lead strips to ink wells to all kinds of paraphernalia that were made of lead on ships, partially because they were so easy to work and recycle essentially without the use of having a furnace, which obviously on a wooden boat particularly you're not going to have. Lead is also very soft, which also makes it a very good material to record inscriptions, details, writing, etc. So that softness also, for thousands of years, it was used as essentially a writing tablet. Instead of refining paper, you could use a hunk of lead and carve your inscription into it. You could also pretty easily polish it out and start again. So kind of an early slate. It also is a very popular alloying metal because it has such a low melting temperature. Lead itself as sort of a pure metal is not very good for a lot of reasons. It's not very strong. It is very soft. Those can be to its detriment sometimes, but we do find lead often put into other mixtures or other types of alloys, things like pewter, for instance, and bronze. You have leaded bronzes, and these help change the properties of these other metals that make them more workable, oftentimes helping to lower the melting points of these metals so they're more easy to cast and work with as well. So it is also a very good alloying material. It's also a very good solder, which is what this image is as well. So things like stained glass, things that help kind of basically glue other types of metals together. It's a very good source of solder. Another thing that makes it a very popular metal to use is that it survives very well in the environment, both in terms of the burial environment when it's buried archaeologically, as well as just sort of in the atmospheric conditions. Another reason why it was very popular on ships is that it did not corrode the way that other metals like iron would, for instance. And a lot of that has to do, and a lot of that is a little bit counterintuitive because based on what we call the electrochemical series, which is basically a determination of how readily a type of metal corrodes, essentially. It's basically a basis of, in comparison to hydrogen as sort of your baseline, how likely is your metal going to either give up or take up electrons. Giving up electrons essentially means, tends to be that metal corrodes. You can kind of think of it as a battery in terms of electrical charges, how with the negative voltage up here, how likely is your metal to be an anode in a battery versus a cathode? Anodes tend to preferentially corrode, whereas cathodes tend to preferentially become reduced or basically build up at material. So this is important to know in terms of the thermodynamics of corrosion, which I'm not going to bore you with too much today, thankfully. But just sort of the gist of this slide is just to get you an idea that under normal sort of in the Platonic ideal of lead, it corrodes very quickly. As you can see, it is a negative an electrochemical series, so it tends to give up electrons pretty easily when exposed to atmospheric conditions. So it's giving up to oxygen, to water, etc. So based on the thermodynamics of lead, it should corrode pretty readily. However, it doesn't actually happen, and that has to do with the fact that most types of corrosion products that form atmospherically, so just like in normal conditions, in oxygen, with a normal amount of humidity, moisture, etc., or in most burial environments outside of really strong acid or basic environments, you have the corrosion products that lead forms tend to be very stable products, which means they're very low in porosity, and most importantly, they're not very soluble in water. And if they're not very soluble in water, that means they can't be broken down easily by atmospheric moisture, for example, and continue to corrode further. So to kind of give you an idea of what this looks like, these graphs over here are called pour boy diagrams, and basically they illustrate under what conditions, both in terms of electronically, so this is basically cathodic versus anodic, so conditions and pH, under whether or not a metal will essentially corrode. If it will be immune, essentially nothing will happen to it, it'll be inert, or if it will produce corrosion products that we call, that will pacify the material, that essentially prevent further corrosion. This chart kind of gives you some examples where you have your metallic lead here at the bottom. You have your sort of your corrosive conditions right here. So these are the conditions sort of in terms of electronic forces as well as pH forces that are driving these reactions. And you can see that there are certain types of products such as lead dioxide and various forms of lead carbonates, which form very readily in most conditions, as you can see. And these are the products that I'm going to demonstrate right here. They form a passivating effect on the metal, which actually protects them and prevents them from corroding further. So here we have our metallic lead right here. We have sources of water, we have sources of heat, and we have sources of atmospheric oxygen, which are going to prompt what we call galvanic corrosion. And galvanic corrosion is essentially the inception or creation of an electronic circuit within a piece of metal that is moving electrons from one place to another. And what happens is that it's moving electrons from your metal, your base metallic lead here, to an area on the surface which is more electronically positive. So you have an anode and a cathode, and you have electrons being passed between them. And as a result, you're going to get corrosion. And that corrosion is going to create the breakdown of your metallic lead, and it's going to produce what we call lead cations, which are positively charged ions. So ions are atoms with a charge. Cations are the positively charged ones. Most metals produce cations. So there are two forms of lead. There's lead 2 and lead 4. Lead 2 is slightly more stable. Lead 4 tends to break down to lead 2. We won't get into too much about that. But you have essentially, you have the gist, corrosion happens, you're having this production of metal cations that are then being exposed to other things in the atmosphere, your CO2, oxygen, et cetera, things that then react with them to then form corrosion products, including things like your platernite, which is the beta version of your lead dioxide, and litharge, which is one of lead monoxide, and also cerussite, which kind of again is that mineral that we talked about a little earlier, and it's one of our lead carbonates. So these are materials which are readily formed out of just stuff that's hanging around in the environment that is then reacting to these metal cations that are being released through this galvanic corrosion of the metal. And these materials then form on the surface, and what they are is that they are then very insoluble. So basically they're not being broken down very easily by things like water, which is the most abundant sort of electronic solution that you have, as well as they're not very porous. So they don't have natural holes in them, essentially. So that you're not getting things passing through them like oxygen and water to then further attack the metal underneath. So it basically forms the shield that essentially kind of other agents of decay, as we call them, can kind of bounce off and don't affect the metal. And this can severely slow down the deterioration of your lead artifacts. So basically it forms a crust of a protective type of lead mineral or lead corrosion product on the surface, which basically stops further corrosion of that metal, and it will be protected from corrosion for as long as that crust persists. So again, another reason why lead has both survived from thousands and thousands of years ago in burial environments, and also why people like to use it. Since it was a very hardy mineral, a hardy metal to use in a lot of situations, which would otherwise, you'd have basically a shelf life on how long you could use your iron, your copper, et cetera. So to just sort of summarize the reasons that lead is so prolific in sort of the artifact and archaeological record in terms of stuff that we find from shipwrecks in particular, but from other types of material culture that have survived for thousands of years, are because of these properties of lead: the low melting point, the malleability, or that ability to work it at cold, the relative softness of the material that makes it easy to decorate or to inscribe or to prettify in some way, its use as an alloying and bonding agent, and also the fact that it has a high resistance to corrosion and it just tends to survive. A lot of stuff just doesn't survive in the burial environment. So the fact that we have so much lead from so many cultures from across the world throughout time really kind of speaks to the importance of this material in an archaeological sense, and also why we have so much of it in a museum like this. And this is just kind of just making the point of all types of materials which have been recovered from burial sites across the world of various types, both alloys as well as lead products themselves. So in terms of what we're really looking at today is we're really going to focus in on sort of that softness of lead, that malleability, and the fact that it often is inscribed with information of some type. And as archaeologists and as curators and as people who research this material want to communicate why this stuff is important to you, our audience, as well as, what does this stuff have to tell us about the past, the fact that lead is so soft and thus can create a physical record of stuff is very important. And this can be both intentional information. So obviously we have things like writing, we have decorations that show some sort of symbolism. This is a lead sarcophagus that is decorated with these, symbolic icons essentially that can communicate information about what the culture thought was important in various contexts. Obviously, you can have things that are just really decorative and pretty to look at, so it can tell you something about aesthetics. It can also provide you information. This is a cloth seal, for example, with some initials. It can tell you, information about names. It can give you dating information, which is always very important. Archaeologists are really obsessed with dating information because that's really how we determined where things came from and when it was used, by finding things in the same layer of burial that have dates associated with them somehow, either because this material was only produced between certain time periods, or sometimes you get lucky and you have something like this bottle seal where you have a big old date stamped on it. And then you also have kind of information. I think this is a good example, is the slingshot projectile. It's from the 1st or 4th century of the Roman period. And just to blow it up, you can see that there's this kind of remnants of an inscription over here, which supposedly are the numbers, the Roman numerals X for 15 or 14 essentially. And we don't really know exactly what this means. It is a fragment, but it's very intriguing. Why is the number 15 on this one little bullet? Does it have something to do with maybe the legion or the cohort this came from? So it kind of gives you tantalizing clues as to the context a lot of these artifacts belong in. Artifacts by nature are basically a broken up piece of a story that we just have a piece of. And so we're always trying to put those pieces back together so we can tell a more cohesive story about people in the past, how they were living, how they were using things, etc. So, being an archaeologist or a curator in a museum like this is being a detective, where you're trying to use material culture to tell a story. And oftentimes you have very fragmentary information like this, but it's very important for that reason. And you can also have things like maker's marks, things that are intentionally put on there that give us information about who was making these, how they were being made. Were they being made in a workshop that employed like 50 people? Were they being made out of someone's basement, essentially? This is an example of window caming, which we'll come to some other examples later. This is a pewter plate with an example of a touch mark, or basically a mark that indicates that this was inspected at some point. And then you also have more incidental markings. We have, since lead is so soft, it often holds things like tool marks really well. So we can tell information about how these materials were made sometimes, or how they were being used based on content, like gouges and impressions left by tools that were being used. We also have just sort of dings and scrapes and signs of use. This plate, for instance, you can actually see that there are cut marks on the surface of this plate. So this kind of gives you information about, oh, they were using cutlery on these plates, for example. Or this cube has these very interesting little kind of markings on them that obviously communicated some type of information, or it could have been material that was just sort of picked up through its use life and accumulated. We can get things like graffiti. We can get things like, as I said, touch marks and tool marks, and things that can tell us more information about how these things were made, the technology that was in use. They can really capture a moment in time, so they can be really useful. So these impressions that are left on this lead are very important to us to try to understand and maintain. As they, to summarize, tell us something about the aesthetics of a culture. They can tell us intentional information that people were trying to communicate about themselves, about their societies, about events that they were living through and experiencing. They can also capture names and dates and informations that can really help kind of build a picture and a timeline for these artifacts, as well as information about how they were made, used, and modified. So where this gets tricky is that, well, a lot of things like lead oxides and lead sulfites and sulfates produce a very kind of thin layer of protective corrosion crust, as an example with this lead apron. There are other types of corrosion that can be a little bit more voluminous, like a lot of the carbonates and the acetates, we'll get to it, as well as just material from the burial that has stuck around and become incorporated into that corrosion product, as you see with these concretions. So these are artifacts that have come from a burial environment, and they are covered in a dense concrete-like material that we call concretion, which is essentially natural concrete, which forms on metal artifacts, often in burial environments. So as you can see, a lot of this material, though in some instances, it actually produces a very even, almost nice patina surface that can be very attractive in its own right. It can, because it is more voluminous, tend to disguise or obscure this information. So generally with lead, as long as it is not actively corroding, we tend to leave it alone. The one instance where we might not leave it alone, even if it is not actively deteriorating and falling apart, is when we want to see if there's anything on that surface that might be hidden underneath these more voluminous corrosion products, these carbonates and acetates and other types of burial material. So we will at those times make the decision to try to remove this material. And there's also not just sort of products that form in the burial environment, there's also post-burial environment corrosion products that happened in often museum environments. And this has to do with the fact that lead is very susceptible to attack from organic acids. So it is not very soluble in water, but it is very soluble in organic acids, which cause corrosion and dissolution of the material. And a lot of these materials come straight from our own exhibits furniture. They come in the materials that we use to build our cases, our museums. They come from the cases themselves. And what this is from is often things made of wood or that have a lot of formaldehyde in them, like a lot of press boards do. As they themselves will decompose, produce organic acids, which often come from either formaldehyde or from hemicellulose, which is a type of cellulose found in plant-based material. And these organic materials will then cause deterioration of lead artifacts that are encased inside them. And how that works is that you can see easily from this nice handy diagram is you have your ancient corrosion layer. So you can take this as your passivating layer. This is that crust that I was talking about that is protecting that core metal. However, you start having organic acids build up in the environment. They're depositing on top of this layer and they're starting to build up, and then they start essentially eating away and creating holes and creating basically dissolving that layer, creating little holes, and also eventually creating these pits in the surface. So first of all, you first lose a layer of material, but then you're also eating away into the material that was formerly being protected by this crust and creating more damage, essentially, both in the form of physical damage, loss of material, as well as what we call pitting corrosion. So you get these little pits and reservoirs that form that then just sort of collect moisture and collect those acid vapors inside of them, which then can just sort of create exponential types of corrosion. So then you get these new corrosion layers that form often underneath the old ones that often result in losing that protective crust and any information they might contain as well. And this is often cyclical. So this is kind of self-sustaining. So this is something that we definitely keep an eye on. And these are also products that we want to remove. Most conservation treatment for lead either involves cleaning the surface so we can see what it looks like, or cleaning the surface in order to stabilize it, to try to remove any type of corrosion products that might contain these organic acids, so this doesn't happen, essentially. So how do we do this? Well, we can do it mechanically. How we do it mechanically, obviously, we can start very kind of gently with brushes. We can then move on to hand tools like scalpels and dental picks and things of that nature. And if we really want to get heavy duty, say there's a lot of concretion covering our lead, we'll use special power tools called vibro tools. Examples of this include paleo tools, as well as air scribes that essentially use compressed air to operate a little needle that can very quickly and with great precision and detail in some instances pulverize anything we don't want to reveal what's underneath. However, of course, the biggest problem with mechanical cleaning is that lead is very soft. And in the course of your mechanical cleaning, you could accidentally, unintentionally damage the surface, add scratches and information that is not there, as well as actually destroy the thing that you're trying to uncover. So mechanical cleaning is used very, very sparingly with most types of lead, and we don't really rely on it to get those voluminous, crusty materials off the surface. Another technique we can use is electrochemical cleaning. So electrochemical cleaning basically uses electrical energy to essentially transform our corrosion products either back into metallic lead or into more stable corrosion products. It'll take that lead acetate, which is a reservoir of acetic acid, and transform it into something more like a lead oxide, which is a lot more stable. So to kind of illustrate this, here's our core metal. Here's covered in some protective corrosion layers with some also not particularly favorable acetate layers as well. We're adding electricity, so we're using it as So we're putting it in a solution. Usually most electrochemical solutions are basic or acidic in nature. So we're creating an acidic, a basic environment, which is causing dissolution of some of that material. So we're getting the production of lead ions. We're then adding in electricity. So basically we're feeding electrons into the system, which are then being fed into these ions, which are then essentially turning into stable solid lead, which can fill in these gaps in the surface and deposit on the surface, and is also, as well as more stable corrosion products, which is helping to consolidate or stabilize the surface so we don't lose it, and it's turning into something that is more favorable to the environment that is in. It's also producing hydrogen gas, which can also basically kind of pop off anything on the surface that we don't really want there that's very lightly adhered, like the corrosion products, etc. So this is oftentimes a very efficient way to remove stuff on the surface of the lead that you don't want. However, electrochemical cleaning can be very hard to control. There's a lot of factors that go into getting it just right so you don't accidentally dissolve your lead, for instance, to maintain basically the polarity that you need in terms of electronics so that you get things moving in the direction you want can consume a lot of energy and resources. And oftentimes you can't really predict the outcomes. You can accidentally deposit too much lead on the surface, for example, especially solid lead, which can sort of have the effect of covering anything on the surface that you might have wanted to look like when we're looking at inscriptions or tool marks and things like that. So it does change the surface a lot. That is kind of the one drawback to electrochemical cleaning. And so in the course of trying to clean your artifact, you can accidentally cover or destroy the thing that you're trying to save, essentially. And then there's chemical cleaning, and chemical cleaning refers to basically the use of acids and bases to then dissolve, much like in nature, the example of the process of that we didn't want happening, where we have acids forming on the surface of our protective crust in our storage or display environments, for instance, and then causing dissolution of these layers and then corrosion of the material. It's the same process, except we're using it for our benefit. We're capturing chemical energy essentially to clean that surface. And these are just some examples of various techniques that are pretty common. You can use acetic acid, ammonium acetate, hydrochloric acid is a pretty common one, believe it or not, Rochelle salts, and chelators like EDTA, which we're going to be talking about very soon. But just to kind of give you an idea of what I mean by the solubility of materials. So a material that is soluble in water means it is able to be broken down by water. Essentially, water molecules are able to dissolve the bonds that form between solid matter. So when you have something like a salt crystal, so like table salt, you have an ionic bond that is formed between your chloride and your sodium molecules. And what happens is that this is a very strong bond, whereas the forces that govern water is pretty weak. You have things called, there we go. But water is a polar molecule, which basically means it has areas where it is slightly positive and slightly negative due to where most of the electrons are spending their time around the atom. And on the whole, these are a lot weaker than the bonds that are keeping your chloride and your sodium together, for instance. But because there's so many of them, and because water itself is existing in this constant dynamic state of being water, but also hydroxy and hydrogen, hydronium, these other versions of itself at the same time, many of which have much stronger charges, it can actually do a lot of work. In a lot of instances, the totality of these interactions are enough to actually break the bonds that form between the your salt crystal, essentially, and then have it dissolve into solution and form bonds with the water instead. However, things that are insoluble, that does not happen. And this does not happen for a variety of reasons, which include the fact that sometimes the thing you're trying to dissolve is just really friggin' big. That happens a lot with things that are in ring structures, benzenes, that have a lot, that's a very big structure, and they have a lot of stable bonds, which include double bonds, so they're super strongly bonded together. And also, as you can see, they don't really have a lot of areas of natural polarity, so there's not a lot for the water to interact with. There's also things that they might be partially soluble in water, which means they break down to a point, such as the breakdown of lead oxide in water. It does break down to monoxide. However, that's about as far as it goes. So you can have things that decompose, but they don't decompose enough. And the thing they decompose to is also insoluble. So you don't get, water cannot do anything to it. You also have hydrogen bonds, which is one of the properties of water that make water such an amazing material in its own right. However, it also means that a lot of times the water has a higher affinity for itself than it does for anything else. And it's sometimes hard to overcome that. And then you have the idea that you have water, which is a good oxidizer, which means it can cause corrosion. It wants to take electrons from things. But then you also have an example of your lead dioxides and monoxides. You also have oxygen in this foreign formation, which is also a strong oxidizer itself. So you kind of get this tug of war happening where basically one oxygen can't overcome the other. No one's getting those electrons essentially. And then you have the fact that lead as a solid form is just not very soluble in water itself. And essentially this, in normal water conditions, also water has a lot of other stuff in it. There's microbes, there's other dissolved salts, and generally harder the water, the more stuff is it, the less soluble lead, especially as a solid, tends to be in it. Just because there's too many other things happening for it to overcome, to break down. There's too much other competition from other things. So we will talk a little bit about in the future why we use tap water for certain things instead of using a really filtered form of water, which we often like to use for other applications, things that are, RO water or deionized water. And we do that because there's deionized water in particular, there's nothing else in there, it's just water. So you have a lot higher chance of your lead-based materials, particularly your lead solids, dissolving into that than you do into your common hard water, which is full of other stuff, which is sort of taking up room, taking up space, and sort of competing for those bonds. All right. So what changes solubility? How do we get something non-soluble to solubilize in water in an aqueous system, for example? And we do that by essentially creating an acidic or basic environment, which basically means you add hydrogen atoms, which are also known, which are kind of shorthand for adding protons or sources of positive charge into your solution, or you add hydroxy ions, which are sources of negative charge. And essentially, this is chemical energy. So when we talk about chemical energy, we're basically saying we're shoving ions of some kind in here that either have electrons or they have protons, and they're going to do work. They're going to shake up the system. They're going to do something. So when it comes to lead in particular, what we do is essentially you basically you put lead or any of these lead corrosion products into an acidic solution. You have a bombardment of chemical energy in the form of your protons, aka your hydrogen atoms, which all of a sudden become very good oxidizers in their own right and are able to compete for these bonds just by the sheer number of them and how much power essentially they contain. So essentially, these atoms are able to help overcome these otherwise very stable bonds between these insoluble materials and help dissolve it and break it up so that it can go into solution. Any questions so far? All right. But of course, the drawbacks of chemical cleaning are the fact that you are using an acid, and as we talked about a little earlier, too much of an acid, you can actually also sort of mar the surface, remove material, basically destroy the thing that you're trying to protect as well. So we always have to keep in mind that essentially we want to use acids, but judiciously in concentrations or amounts that we can kind of control the outcomes a lot easier. And that we also have to really make sure that we're able to remove as much of that acid after the fact as well, because if we leave it on the surface, then we get that corrosion cycle based in acid attack again. All right, so just to kind of go back to this slide. So those are sort of the ways that chemical cleaning works. We're going to be talking about a very specific type, which is known as EDTA, and this is what we call a chelator. So a chelator is of what we call, it is a type of molecule that we call a ligand. And a ligand is an ion or a molecule with a functional group that is able to bind to a single metal ion. And it's composed of essentially a hydrocarbon backbone, which means it's basically has a backbone that is formed of carbon and hydrogen atoms, and it has at least one functional group And that functional group is what makes a molecule able to do something, essentially. It gives it some sort of extra special superpower or property that allows it to do work in a system. And a lot of times what it does is it allows it to form a charge, a negative or positive charge that can basically use as a form of chemical energy to essentially cause chemical reactions to happen or participate in chemical reactions. And EDTA in particular is a type of chelator or ligand called a polydentate ligand, which basically means it has multiple functional groups that can basically work together to isolate and bind to a single cation still or a single metal ion, forming what we call an organometallic complex. These are often used in biological systems. They are naturally occurring. EDTA is an example of this and is also man-made. And kind of going back to the name, why do we call them chelators? And that comes from the Greek word chele, meaning claw. And as you can see, it's kind of analogous to a crab claw, kind of closing around a metal ion. And just kind of give you a visual. Unfortunately, my GIF is not looking, but this is kind of what I envision, sort of what it's like to be a metal ion being sort of scooped up by a chelator is to basically be everyone, the claw. Yeah, exactly. So if you take nothing else away from this presentation, please just know that chelator equals the claw. All right, so how do chelators work? So chelators themselves are acidic salts, and this means that as a solid form, when they are put into solution and they dissolve, they deprotonate, which basically means their hydrogen atoms are released. And as we just discussed, hydrogen atoms being introduced into a system increases the hydrogen concentration and lowers the pH. So it makes the conditions more acidic, which can then lead to the breakdown of otherwise insoluble materials. The example given here is calcium carbonate, which is only partially soluble in water. However, adding a chelator helps break this down further. By adding acidic conditions, you essentially dissolve your calcium carbonate into its component parts, which can then go on to do other types of work. Barium sulfate, however, is insoluble in water. And what chelators can do is that there's kind of a two-part process. It's that dissolution. It helps, it adds acidic, it makes the environment acidic. It helps break up these materials. And then in the case of the barium ion, you have all these metal cations sort of floating around that the chelator can then sort of glom onto with its claw and complex around. So you have two different sort of methods. And once the barium ion is sort of in this complex with the chelator, it becomes soluble essentially, because the chelator itself is water soluble. This metal ion is now part of the chelator, and it can now go into solution and be washed away or dumped down the sink, etc., or used to do other work in solution. So it is different ways. Basically, chelators are used to get insoluble things into solution that would not otherwise go in by themselves, both by affecting the pH, but also by binding to them and making these organometallic complexes, which are water soluble themselves. Which is, we also call this, I got a little ahead of myself, this process is called sequestering. Sequestering is that sort of isolation of these insoluble metal ions that allow them to go into solution. So looking at, so this is EDTA. The full name is ethylene diamine tetraacetic acid. It's a mouthful. Also known as why we call it EDA, because that's a bit of a mouthful to say. And it is a polydentate chelator, as we ligand chelator, as we meant before. So we have over here, we have our hydrocarbon backbone with various functional groups. And then we have right here our two functional groups with the sodium attached to them. And the version, I back up for a second, the version we're talking about, there are various different types of EDTAs that have very different additives to their functional groups that lets them do slightly different things. The one that we're going to be talking about today is the type that is known as disodium salt dihydrate, which basically means it has two sodiums in its functional group, and those will be important later. So this is our structure. So this is our backbone over here. These are the two functional groups that are going to act as our chelator arm, which are going to be the claw. So this is sort of giving you an idea of what that structure looks like. And this is a three-dimensional model that kind of puts in perspective what this looks like as a macromolecule. So here are our claw functional groups over here. All right, so EDTA itself is an interesting molecule. As I kind of alluded to earlier, there are a lot of naturally occurring chelators. A lot of them exist in our bodies. That's what a lot of our amino acids actually do, is that they chelate things to make them soluble in our blood and make them able to do various tasks in a biological system. However, starting in the 1960s, we started manufacturing our own chelators. We started designing and making our own, including EDTA. EDTA originally was actually designed to be a chelator for nutritional supplements, interestingly enough. However, it was a little too good at its job. It was a little too stable to be able to be metabolized and broken down by the human body, and it had no nutritional value, so it wasn't being absorbed into the body, so it was just being expelled. And also it tended to be such a good chelator that it tended to strip mineral content from the body, which we wanted to keep. So it had very limited sort of uses for the function for which it was originally designed. However, since then, we have figured out ways of making EDTA work for us in different types of functions. Commonly, you will find it as a preservative, a color fastener, an antioxidant, and even a flavoring agents in a lot of food and cosmetics. And it also very famously has a very important biological use, both as an anticoagulant, so something that basically stops you from coagulating, so basically takes up platelets essentially, and also in chelation therapy for heavy metal poisoning, aka lead poisoning. And that is mostly what you'll hear the context of EDTA being used in, outside of the conservation context I'm about to explain. So it is being used as a way to basically take lead out of your bloodstream once it's in there. But how EDTA works in a system is that you have our EDTA molecule over here. So here's our two sodium groups, and here are the hydrogens that when they are put into water and dissolved, deprotonate. So they essentially disassociate from their molecule. They go into solution, which of course creates acidic conditions. So the solution for EDTA is generally a low pH, and it usually lowers the solution between 4 and 6, which isn't too severe. It is still pretty weak acid. And again, since this was designed for use in biological systems, that kind of makes sense that we don't want it like so acidic that it burns us from the inside out or something like that. So you have your deprotonation that happens, which creates your decomposition products or your dissolution of your various types of lead corrosion products into sort of more digestible ions, which then end up being sequestered by your chelating agent and then able to be removed essentially from play by being dissolved into the water as a result. And as you can see, the sodium still is hanging around here, and the sodium plays a pretty important function as well. For instance, these will, in order to get that chelator operational, these sodium ions have to essentially leave the structure. They have to dissociate. They themselves have to go into solution and do other work. So then you leave these kind of activated oxygen molecules at the end of this function group that can do work and bind to these metal cations. So these do a very important job of disassociating to both open up that chelating agent, and they also create a buffer, because in water you have a lot of hydroxy ions, so you're also getting some amount of sodium hydroxide, which is creating a natural buffer, which in itself, the more hydroxy ions you have in a solution, actually oftentimes the better your chelator works. So a lot of times people will add sodium hydroxide into their chelator solutions containing EDTA in order to increase the pH to about 8.5 in order to add these more hydroxy ions, which more effectively remove the sodium from which you can kind of think of it as sort of the, I guess, the safety on your chelating arm. So the more of those remove, obviously, the more chelating arm function you have and the more metal ions you can bind to. So this is sort of a self-perpetuating system of formation of sodium hydroxide, which then breaks apart into hydroxy atoms, which then basically remove your sodium ions, which then open up your chelating arm so that it can act as a claw and snatch up and sequester your recalcitrant little lead ions over here. And in the process, you're also having, especially for the break, you're also producing various types of gases. This will be important later on because it's one of the ways we can determine that our chelating therapy of our lead artifacts is working by the creation of bubbles. And you will see this in action in a few minutes. But hydrogen gas is very common. And also if you're breaking down lead carbonates, you're also getting a certain amount of carbon dioxide produced as well. So at the moment, I'm going to share with you, hopefully, a video I put together where I actually use an example from the lab. So an artifact that we have treated with our chelator EDTA. Oops. I think I actually. How do I hit play? Sorry. And the technical difficulties continue. No, I spent so long on this. All right, moment. Might need a moment to load.
I was gonna say, just try hitting your space bar.
I think it's trying to buffer.
Michelle, can you hear me?
I can hear you, yes.
Try hitting your space bar.
I did.
And it didn't do it.
It's attempting to buffer. Unfortunately, this is PowerPoint on the web application and on the desktop, so it's sometimes very slow to do things. So it was working before. Hey, Christine, how do I get out a laser pointer?
I think
just
you
get
just
a
click
regular
laser
mouse?
pointer. When you bring that menu back up, can you just click
Oh, there
laser
we go.
pointer? Yeah.
There we go. That's what it was. So sorry. All right, so these are mini balls, which are a type of bullet very common in the 19th century. These were provided by our curator, Mike Caraway, who is a Civil War aficionado. And as you can see, a lot of them have a very distinct patina formed on them from probably lead carbonates by being buried in the environment. And for science purposes, we're going to remove that. So, oops, why is that going so fast? All right, so we have put our mini ball into a solution of EDTA. It is a 5% solution, and we're going to leave it in there for about 2 hours. And what I want you to pay attention to are the evolution of those bubbles, that hydrogen, that carbon dioxide, and other gases, which are forming on the surface. As you can see, the more chemistry that is happening, the more bubbles you're going to get. Over time, as this crust slowly starts to dissolve and deteriorate, those bubbles will start to dissipate and you won't get as many. So what I'm doing here is essentially, it helps a lot of times as we're buffering. EDTA is pretty good at dissolving a lot of things, but it often doesn't dissolve everything. So to help it along, a lot of times we do use a little bit of mechanical abrasion and cleaning to essentially try to help remove some of that kind of softened up and still partially attached material on the surface to help clean it up some more. So a lot of these treatments, we do use aspects of a lot of the things I talked about with these, usually not, you often use a lot of different techniques together to try to get the results you want. All right, I'm just going to pause this for a second. But as you can see already, there's a lot fewer bubbles, so you can see already how much of that crust, that patina, has been lost, how much of that lead substrate is now peeking through, and also how few bubbles are now gathering on the surface. We also have, there are other ways you can sort of tell that your chelator is working. A lot of times the solution, as it becomes more saturated, depending on how many ions it is capturing and sequestering, will change color. I originally actually had a slide in here that showed you the waste product of this process that was basically bright urine yellow, essentially. It's lovely, but it was a little gross and I decided not to do it. So. But yeah, you can really see it happening, especially on the bottom. So hour-and-a-half benchmark, still going, still got bubbles going. This is actually a very short video, but it keeps buffering, so. Anyone have any questions while we wait for this thing to buffer?
Is any of this dangerous from a human perspective, a health perspective, when you're cleaning this or developing it?
That is a good question. Obviously things that are acidic can be, irritating or can burn your skin in particular. Obviously, we don't really want to ingest something, especially if it contains a chelator, without, supervision or, medical intervention, except, it's a medical process. We definitely don't want to ingest EDTA ourselves, unless it's been rendered in a way as it is with a lot of food products and cosmetics and other types of things in a way that it is inert in the human body, essentially. But for what I'm doing, I always use personal protective materials, so PPE, personal protective equipment, the most basic of which is using nitrile or chemical resistant gloves that lets me handle this material without getting it on my skin and which won't eat through the glove as well. So that's a big one. This entire process was also done in a fume hood. So a fume hood basically is able to draw out or capture organic vapors. So if the EDTA, for instance, for whatever reason, the solution became aerosolized and I didn't want to breathe it in, my fume hood would essentially extract that and take it outside where it could be dispersed and diluted a lot more than it is in my lab. But for the most part, EDTA is pretty mild, especially at the concentration we're using. We typically don't use anything higher than a 10% solution in the lab. And that's pretty true of most kind of solutions of this type, that you don't tend to use you tend to use the lowest concentration of material that you can get away with, partially for health and safety reasons. So you're not needlessly exposing yourself for things that could potentially be dangerous in the wrong environment. Does that answer your question?
Yeah, it does, lead in the water is a big, has been a new poison.
Yes. We don't drink the water. That's a big one. We're not ingesting the lead, and we're not basically lead is dangerous when you either inhale it or you ingest it, essentially. And generally, heavy metal poisoning, like lead poisoning, is accumulative. So it's something that is built up over a long period of time. So if I was consistently, drinking my EDTA water, that'd be pretty bad. But for the amount of exposure I'm giving myself, it should not be a problem. And again, nothing's being aerosolized, so I'm not breathing in lead particles, and I'm definitely not ingesting this. And that's also why it's important to do things like wash your hands, wash any of exposed skin or clothing that has had contact with the solution. See if I spilt it, or you can see my hands are a little wet just from handing the bullet, for example. Dispose of your gloves and to just make sure you wash everything out and rinse it thoroughly. And that's actually the next step of this video. In which it is very EDTA, sometimes we have problems with not thoroughly rinsing it enough so that we remove all that residual acidic content, which can lead to further corrosion. So it's also very, very important to rinse the artifact thoroughly. Usually you rinse it for about the same period of time that it was in treatment. So if it was in treatment for 2 hours, you need to rinse it for at least 2 hours, sometimes more. Sometimes you can leave them in for 24 hours just to make sure that you've really diluted down any acidic content that's still there and removed any of that chelator as well.
So what kind of a rinse?
Rinse, it's just a tap. It's just tap water rinse. As I sort of alluded to earlier, hard water is better for lead if you're trying not to dissolve it. Essentially, soft water, you have a much higher probability of actually dissolving even solid lead, which is typically pretty water insoluble, just because you don't have anything else in the area that is competing for those interactions with the water. So it's all focused on that lead. Heating your water, and that's why when it comes to lead pipes, new lead pipes that have not formed a protective scale on them from oxides and carbonates, that you're kind of forcing hot water through, tend to be the worst in terms of potential lead poisoning or contamination from drinking water. Very famous example is the water filtration system on the Terror and the Erebus, the Franklin expedition from 1845-48, which mysteriously disappeared in the Arctic until recently we discovered both ships. They had at the time state-of-the-art filtration systems, but they used lead pipes. And because those lead pipes were new and hadn't yet developed a scale on them to protect the lead substrate and prevent it from directly dissolving into the water. And because they also had a hot water system essentially on board ship, and they were basically, using ice melt and heating that for drinking water and things like that. They were forcing hot water through new pipes that had no scale on them. And that's one of the reasons that we think they might have suffered from lead poisoning. And also, it's also very important to dry your artifact thoroughly to remove, again, any water deposits, especially any water like microscopic water, which is caught in the reservoirs on your surface, any imperfections, any pits, things like that. You can get very, very tiny pockets of water, which can then become pockets of chemistry. So those can basically cause corrosion essentially. So you can do this slowly in a controlled manner where you basically use something like a desiccation chamber where you can very slowly and incrementally remove moisture and dry your artifact. Or you can do it just sort of, as you saw, I cheated. Basically, I used a hair dryer to do it. If you just need to dry something very quickly and very thoroughly, which typically we try not to do, but for basically expediency's sake is what happened here. So you can see the before and the after example. So this is our bullet pretreatment, and you can see exactly just how much material that EDTA was able to remove. And this is comparison from our finished treated project with one of its untreated compatriots. So again, you can kind of see the differences in the surfaces. And, if unfortunately there's not any particular markings that you can really see on the surface at this point, but if there were, they'd probably stand out a little bit more. All right, so there are problems with mitigations, as we sort of alluded to. Waste products, toxicity can be a factor, but we do take steps to try to reduce those risks by either proper waste disposal and holding. How I get rid of my leady water essentially is I often just let the water evaporate it off and then just kind of, essentially thoroughly clean the inside of the jar. So, let all that material precipitate into a solid, and then it can be kind of isolated and disposed of in its own regard. But sort of the problems with EDTA specifically is it is a weaker acid. It may not be able to break down all corrosion products, unlike hydrogen chloride, not hydrogen chloride, hydrochloric acid, which is obviously a much stronger acid and can break down most things over given enough time. It also has high affinity, as sort of the original sin of EDTA and why it was not really used as a health supplement anymore, is that it is very, very good at binding to those metal cations, which it has an affinity, and lead it has a very strong affinity to. So you can very easily overdo it if you use too high a concentration. If you leave it in there too long, you can remove too much material, and you can basically start stripping lead off from the surface of your artifact, which kind of defeats the purpose of trying to, preserve that surface and make it more legible. And EDTA, especially because it is an acid, if you don't thoroughly remove it from the surface, it can induce future corrosion and damage the artifact, as we've sort of discussed with those atmospheric acid attacks from organic acids in our display environment. Yeah. So these are just examples of, you can see there's still a little bit of corrosion product in those grooves that the EDTA was just not able to remove. However, it had already been there for 2 hours. Most of the surface was exposed. I didn't want to overexpose it, which is why I chose to remove it from solution at the time that I did. But these products still are persistent there. This is an example from a study I did on EDTA treatments like 6 years ago, where you can sort of see the surface changes between the treatment and after the treatment. You can see there has been some polishing of the surface, some erosion essentially of the surface from the treatment process. And this is another example from that data set in which we did have a few instances where we did get some sort of renewed corrosion products that are forming. You can see these little pits right here because there's still some residual acid that was left on the surface and they weren't rinsed thoroughly enough. All right. So how do we mitigate this? Well, we can increase treatment time or EDA concentration. And again, we can kind of couple it with another type of cleaning process, either mechanical cleaning. I've never tried it with electrochemical cleaning, but you probably could in order to remove, or other chemicals to remove additional products as you see fit. In terms of damage, a lot of it kind of comes down to what do we consider damage? What is significant? What is an acceptable sort of threshold or magnitude of change we're willing to accept with these treatments to get what we want out of them? So you can see these are comparison of the before treatment and after treatment of these details, where you can see that this treatment did affect a lot of the surface in some place. There's material that's missing, there's material that's been changed, there's materials that's been eroded away. But if I told you this was taken at a magnification of about 600 micromils, that might kind of change your perspective of exactly how much of an effect it had on the artifact. Because even though it definitely had an effect, it's so microscopic that when you zoom out to kind of more of a macro lens, which is what we'd be seeing with our eyes, you really can't tell the difference. And the inscription on this surface is still perfectly legible. So a lot of it has to do with kind of determining, all right, what is an acceptable amount of damage I am willing to inflict on this artifact? How do I determine what that is? And what is my threshold for not doing it, essentially? Like, what is my threshold for not damaging the artifact? And honestly, just because this is from the same study I mentioned earlier, a lot of this erosion that you see here was actually more of an effect of the brushing and the mechanical cleaning than it was of the actual EDTA. So for the most, and of course, rinsing and drying thoroughly is probably the most important step you can take to just remove that remainder EDTA. And also there is this sort of long-term care of these artifacts, the continued monitoring and controlling of the environment. You can do something called, which involves things like AUDI testing, which is a series of tests that are conducted, experimental tests, to basically test how many acidic vapors are in your environment. You can test materials, like any material you want to bring into your museum to use in a case, for example. You might AUDI test it before you actually build with it, which basically makes putting it in a very closed environment with a type of metal that could easily corrode, and seeing if it corrodes the metal. Essentially, that kind of gives you an idea if there's acids around. So these can even be done in cases that are on the display gallery. Sometimes you might see these kind of coupons hanging around, or some other type of experimental thing in there that doesn't really necessarily look like an object. And if you see that in a case, it probably means they're doing some sort of AUDI testing. They're trying to test for organic acids by seeing what the case environment and how it's basically how the case environment is affecting basically uncorroded, non-archaeological materials, non-artifact materials. You can, to kind of also avoid this, you can avoid using the materials that require AUDI testing and create organic acid in the first place. We use a lot more glass and plastics nowadays than wood, for example. You can also keep a pretty stringent monitoring eye on your cases. So things like data loggers, other types of detectors, which can monitor your temperature, monitor your humidity, kind of tell you how much moisture is in the environment, what the temperature is exactly, all these factors that go into leading to corrosion. And then you can also do things that either remove moisture, things like desiccants. You can also put in things that remove organic acids and other types of pollutants like tarnish strips to help reduce the amount of deposition of new acidic materials that end up on the surface. And you can even then coat your materials. That means either your artifacts or the materials that you're putting in your cases, for example. So the conclusions here are that when properly done, EDTA is powerful and sufficient enough to remove most of what in terms of unwanted corrosion and surface crust to reveal surface details. At the same time, it is gentle enough not to significantly damage the artifact, since a lot of times the sort of the damage we're looking at is either very theoretical or it's so minute that it doesn't really have a very immediate impact on visually. This is an example from Jamestown. This is an example of lead caming. I did say that would come up again. So lead caming, these are the lead strips that used to hold individual panels of glass together in a window frame, because back in the day they didn't necessarily have the technology to make really big panels of glass, so they made smaller panels of glass which they would then connect together using these lead slots, essentially these kind of almost like kind of duct tape together with lead, essentially. And this is how this was found in the burial environment. As you can see, it's rolled up really gnarly, it's covered in burial products and corrosion products. It was treated with ETA, and then it was very carefully mechanically unrolled, and you can see, lo and behold, there's actually a date of 1671 on it. So this is something that EDTA treatment allowed us to see and visualize we may not otherwise have seen. All right, well, that is my presentation. Thank you so much for listening. If you like what you heard, please do remember to check out our next installment of the Maritime Heritage Series, which is the story behind Echo the Whale with my good friend and fellow curator, Keith Rittmaster, which will be happening on October 12th at 11 a.m. on 2023. Please skip that typo. Does anyone have any questions? Thank you for listening and for bearing with me, especially through some of the technical difficulties. All right, Christine, we have anything?